In this section, we'll talk about the equations of space curves. Suppose that we have a space curve C, which represents the set of all points x, y, z in space, such that x equals to f of t, y equals to g of t, and z equals to h of t. Essentially, what happens here is if the space curve is represented by the vector equation r of t, that is equal to the vector with components f of t, g of t, and h of t. One other way to think about the vector equation is that it actually represents the position vector that points at the point with coordinates x, y, z on the curve. So the vector r of t is equal to the vector with components x, y, z. And this is equal to the vector with components f of t, g of t, and h of t. So essentially, this is how we get that x equals to f of t, y equals to g of t, and z equals to h of t. And these three equations are called parametric equations of the curve C, and t is called the parameter. Now, suppose that we have a vector equation r of t that is equal to t to the square times the vector I, plus t times the vector j, plus 2 times the vector k, and we're asked to sketch the curve that is represented by this vector equation. From the vector equation, we get that x equals to t to the square, y equals to t, and z equals to 2. So x equals to t to the square, y equals to t, and z equals to 2. And combining x and y, we have that x equals to t to the square, and this is equal, since y is equal to t, is equal to y to the square. So that gives that x equals to y to the square, which represents a parabola that opens in the direction of the positive x-axis, and also z equals to 2. So if we sketch that curve, here we have the x, y, z coordinate system. So we have a parabola that opens in the direction of the positive x-axis and is shifted up by 2 units. So it's shifted up at the plane z equals to 2. And it has a vertex at the point 0, 0, 2. And we can also find the direction of this parabola. So we see that as t increases from negative to positive, as t increases from negative to positive, then y will also increase from negative to positive. So essentially, as t increases from negative to positive, then y will increase from negative to positive. So that gives us also the direction of the parabola, which will be like this. So as t increases from negative to positive, y increases also from negative to positive. So we go from more negative t's and more negative y's to more positive t's and more positive y's. Let us now see another example. We're asked to find the vector and parametric equations for the line segment that connects the points P with coordinates 0, -1, 1, and Q with coordinates 1/2, 1/3, 1/4. The first thing that we need to find here is the position vectors that points at the points P and Q. So let's see, for the position vector that points at the point P, let's call that position vector R0, which is equal to the position vector OP. And this is equal to the vector with components 1, 0, -1, and 1. And for the position vector that points at the point Q, let's call that position vector R1. So this is equal to the vector OQ. So this is equal to the vector with components 1/2, 1/3, and 1/4. Now for the equation of the line segment, we have the general form that is given by r of t, vector r of t is equal to 1 minus t times the position vector r0 plus t times the position vector r1. And we know that this is valid when 0 is less or equal to t, less or equal to 1. And if we substitute the position vectors r0 and r1, we'll have that 1 minus t times the vector with component 0, -1, 1, and then plus t times the position vector R1 with components 1/2, 1/3, and 1/4. So this is equal to, and if we now combine the components, the x, y, and z components, we have 1 minus t times 0 plus 1/2 t for the x component, and then we have 1 minus t times -1 plus 1/3 t. And then for the z component, we have just 1 minus t plus 1/4 times t. And if we simplify here, we have that the vector equation of the line segment is equal to the vector with components 1/2 t, -1 plus 4/3 t, comma 1 minus 3/4 times t. And this is valid when 0 is less or equal to t, less or equal to 1. So this is the vector equation of the line segment. And let's now find the parametric equations for the line segment. So if we express the vector equation by the components x, y, z, we have that this is equal to 1/2 t, comma -1 plus 4/3 t, comma 1 minus 3/4 t. So from that we get that x equals to 1/2 t, y equals to -1 plus 4/3 t, and z equals to 1 minus 3/4 t. And again, 0 is less or equal to t, less or equal to 1. So these three equations represent the parametric equations for the line segment that connects the points P and Q.